Starting with number one, the Boolean algebra problem. Which expressions are equivalent to blah, 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 blah. Okay, let's take a look at our answer choices. You have to check all of them one by one. The easiest way to probably do this is actually to, what is it? Simplify the original given expression that they give us and then see which one of them match. Now, that being said, just looking at the answer choices alone, we know that B cannot possibly be the answer. Um, we can't really wait. Yeah, just by looking at this alone, I guess you maybe could, but you can't really eliminate any of the other. Actually, yeah, you can. Yeah, we're gonna eliminate a few of these before we even start simplifying this down, right? We can eliminate A because B is just an XOR expression, right? We know that this simplifies to A not B plus not A B, right? So that only differs from answer choice A by the existence of the a not sign here, right? And those are not similar enough, or sorry, those are not different enough that they can simplify in any other way. So A and B cannot both be equivalent to both each other as well as this equation up here, right? B, C can also not be the same because they're essentially not versions of each other, right? Whatever we simplify B down to, C is going to be the exact opposite. So we know B can also not be the answer. In terms of C, I'm not sure. I would have to simplify this down first. Well, actually, yeah, no, he can't be the answer either, right? Because we know that this is the exact same thing as writing A, X, or B, right? And we've already, which is exactly the same as I just chose B, and we've already come to the conclusion that this cannot be the same as this, right? They're opposites of each other. So the answer is either going to be D or it's going to be none of the above. Basically, if we can simplify this equation to equal either this or this, then the answer will be D. If it simplifies to equal neither of the two, or yeah, either of the two, then the answer will be E. That kind of just narrows down our choices for us, and it kind of helps you guys, I suppose, be a little less overwhelmed about what this could possibly be. So let's start by ignoring the XOR first. Let's just simplify the extended not bars. That'll leave us with A times not B, XOR not A times B. Right. And then we can do A times not B times the extended not bar of not A B plus A not B and then not bar over top, not A times B. Right. And then if we simplify this further, this becomes A plus not B. And then on the right hand side, this is going to simplify to not A plus B. Right. This is going to simplify to A times not B. Sorry, I'll write it down here where it's a little easier to see. A times not B plus another A times not B. So that's just going to remain as A not B. Plus on the right hand side, this is going to be not A times B plus another not A times B. So two things added together that are the exact same are just going to, well, we're just going to get rid of one of them because we don't need to repeat. This is going to be answer choice C, and as we've already stated before, answer choice C is the same thing as answer choice B. So the answer to this is going to be D. Any questions about number one? No? Okay. Number two, a slightly easier Boolean algebra problem. How many ordered triples make the following expression true? Let's get rid of this extended not bar first. We have to cleave it here at the or sign to give us extended not bar, not A, B, times not C. And then this is going to then give us not A plus not B times not C. This is going to give us not A, not C plus not B, not C. That's going to be the entire left-hand side. That's going to be multiplied by not A, not B plus not C, right? And then we're gonna FOIL this out. This gives us not A, not B, not C. I'm gonna write it up here. Sorry. Not A, not B times not C plus not A times not C plus not A, not B, not C once again. Oh wait. Yeah, once again, that's just gonna be the same. And then not B, not C. So either one of these two can actually cancel out this not A, not B, not C entirely, which means we're essentially going to be left with, wait a minute. I fear I may have done this wrong. Did I do this wrong? Hmm. Oh, no, no, they just did it weird. Okay, anyways, we're left with not A times not C plus not B plus not C. And then if we were to just plug this into order triples, right, the ones that make this true, this first half, not A, not C, true are going to be the ones where A and C are both equal to 0. So that's going to be 0, 0, 0, and 0, 1, 0. And then the ones on the right-hand side are going to be true as long as both B and C are 0, right? So that gives us 0, 0, 0, and uh, 1, 0, 0. Yes. 0, 0, 0 is a repeat in both cases, so that's just going to count as one order triplet, leaving us with a total of three order triplets that make this following expression true. The answer to this is going to be also B. Number three, evaluate the following expression. This is a simple bit string clicking problem. We have an LCirc 10. There's only 6 bits in this bit string here, so we're going to just simplify this to LCirc 4, where we take the leftmost 4 digits and we circle it around. That's going to give us 1, 0, 0, 1, 1, 0. Then we're going to do a not expression to give us 0, 1, 1, 0, 0, 1. An RCirc 2, we're going to take the rightmost 2 and move it to the right to give us 0, 1, 0, 1, 1, 0. And finally, L shift 3, we get rid of the leftmost 3 and add zeros at the end to give us 1, 1, 0, 0, 0, 0. That is going to be answer choice C. Number four, how many different values of x, a bit string of 5 bits, makes the following expression equation true? Let's do everything except for the x part. So L shift 2 of this is going to give us 0, 1, 1, 0, 0, right? We get rid of the leftmost 2 and we add 2 zeros on the right hand side. RCirc 3 is going to take the rightmost 3 and circle it over to the left. That's going to give us 0, 1, 1, 0, 0. So we have x, or well, let's say A, B, C, D, E. We have A, B, C, D, E, and, oops, write that for and 0, 1, 1, 0, 0 is going to give us a final answer of 0, 1, 1, 0, 0. So if we were to rewrite this in like a little easier way to see A, B, C, D, E, let's do that, right? It's going to give us 0, 1, 0, 0. There's a number of ways to do this. We could actually just, solve this as is. Or we could actually, yeah, let's just do it. Sorry, I don't know why I'm making this more complicated than necessary. Keep in mind that this is being ANDed together. I don't have the room, so we're just gonna write it like that. Right. For A and 0, right? If A were equal to 0, I'm gonna write A for and. If A were equal to 0, then the answer would be 0. If A were equal to 1, this A stands for and, not A. If A were equal to 1, then the answer would still be 0. So we can say that A and 0 is going to give us 1. So the same logic applies for the B. That is also going to just apply to 0. What about for B, C, and E? Well, if B were equal to 0 and we ANDed it with a 1, that would give us 0. But if B were equal to 1 and we ANDed it with a 1, that would give us an answer choice of 1. Our answer changes depending on what our value of B is, and it corresponds to what the actual value of B is. So we can say that this is going to just simplify to B. This is going to simplify to C, and this is also going to simplify to E. So on the left-hand side, we have the simplified bit string of 0, B, C, 0, E is equal to 0, 1, 1, 0, 0, right? A and B are negligible. B, C, and E are going to equal 1, 1, and 0 respectively. So we can say that our bit string is going to be equal to asterisk 1, 1, asterisk 0, right? It asks us how many different values of x makes the following equation true. Remember, to solve this, you guys are going to use that formula, 2 to the power of the number of asterisks you have, and in which case you have, wait, what? Oh, I wrote this wrong. Jesus Christ. I'm sorry. This should be zero. Okay, my bad. Sorry. This is zero BC zero zero. Jesus Christ. Okay. Our equation or our bit string should actually be asterisk one one asterisk asterisk. Sorry, we have three asterisks, so our answer is actually going to be C8. All right, number five, recursive functions. I did go over this yesterday, but we can go over it again today. Given the following recursive functions to find the value of a number b raised to a given power e for e is greater than or equal to 0, what definition will give the value of a number b raised to a given power e for e is less than 0 so that 3 to the negative second power gives us 1/9? Okay, this is very wordy. You don't actually need to understand anything in this entire like instructions, except for the fact that if they give you a b value of 3 and an e value of -2, right? It should solve out and your recursive function should output 1/9 as your final answer, right? And yesterday I was talking about how we can choose some of these to eliminate, choose some of the answer choices to eliminate just based on common sense and logic, right? So the one that we are filling out, or the one where we're trying to figure out what equation fits in, is under the condition where our exponent is less than 0, right? Um, in that case, I told you guys that we could eliminate answer choices A and C. Why? In A and C, we recursively call back to the function again, but this time with an exponent that is even further away from zero than we within wherever we already were, right? So if we had 3 to the negative second, for example, e is -2, -2 is less than 0. If we were to plug it in for both answer choices A and C, that would just recursively give us a function that says b comma e -3, then b comma -4, b comma -5, et cetera, et cetera, et cetera, right? Nothing inherently wrong with that per se, except for the fact that that is going to give us an infinite loop, right? We're consistently going back into that third branch where e is a negative number, and we have no way of getting out of it. So the answer cannot be either A or C. Now, between B and D, at this point, it's just a matter of plug and chug, right? Let's assume that the answer is B. Okay. Let's assume that the answer is B, and let's rewrite this to make this a little neater. And in here, we've replaced it with f of b comma e plus 1 divided by b. That is our new function, right? If we were to try and solve this, where f is equal to 3 comma -2, this is equal to f of 3 comma -1 divided by 3. F of 3 comma -1 is equal to f of 3 comma 0 divided by 3. And then finally, f of 3 comma 0 is going to be equal to f of, oh, sorry, no, this is just 1. This is going to be set equal to 1, right? This is then going to give us 1/9. And then this is going to, oh no, this is going to give us 1/3. And then this is going to give us 1/9, which is the answer that we want. And, spoilers, but the answer to this is just going to be B. If we were to plug in our answer choice B, however, right? Let's replace this instead with b divided by f of b comma e plus 1. If we had this instead, what we would instead get is f of 3 comma -2. -2 is equal to 3 divided by f of 3 comma -1. F of 3 comma -1 would then give us 3 divided by f of 3 comma 0. And then f of 3 comma 0 is going to give us 1, right? This gives us 3 divided by 1 is 3. 3 divided by 3 gives us 1. That is not the final answer that we are looking for, so D is not going to be the correct answer. Obviously, though, if you already solved B and it turned out to be correct, then you would have just um what was I saying? What was I saying? If you already did answer choice B and you tried it and it turns out to work, then obviously you just pick B and move on. But anyways, yeah, that's the reason why B is going to be the correct answer. Okay. Moving down to number six. Number six is the recursive function problem, just a little bit complicated looking at first, but other than that, the concept is as before. F of 1 comma 20, oh my God, 1 comma 20 is going to be, in this case, we are falling into our second condition because x1 is less than y, which is 20. So this is going to give us f of 4 comma 18 minus x minus y is going to give us negative 19. So that's really saying plus 19, right? F of 4 comma 18 is going to give us f of 7 comma 16 plus x minus y is negative 14, so that'll be plus 14. Next, f of 7 comma 16 is going to give us f of 10 comma 14 plus 9. F of 10 comma 14. Yeah, f of 10 comma 14 is then going to give us f of 13 comma 12 plus 4. And then once we're at f of 13 comma 12, we end our second branch looping shenanigans and we go back up to the first branch to give us a combined sum of 25, right? 13 plus 12 is 25. When we plug it back in, this is going to give us 29. This is going to give us 38. This is going to give us, I don't know, 52, I think. And finally, 52 plus 19 is going to give us 71. The answer to this is going to be D. Number 7. How many ordered triples make the following circuit true? Very simple digital electronic problem, right? Starting with the first one in like going left to right pattern, we have a not and operator. So that's going to give us not and of B and C, which we can split using De Morgan's law into not B plus not C. This is going to go back up here on the top here. This is going to be added to the A. So we have A plus not B plus not C. And then down here, it's going to be not B plus not C plus C. Now, not B plus C is going to cancel each other out and become 1, which leaves us with not B plus 1, which is also just 1. So on the bottom here, this is going to just simplify to 1, right? Now, we're going to bring it all together with another not and operator. So we have, wait, oh yes. Okay, this is an and operator. So that's going to give us A plus not B plus not C. This entire thing is going to be multiplied by 1, this 1 from down here. But obviously that doesn't mean it doesn't change anything at all. So we're going to leave that as this, and we're going to put an extended not part over top. This can be then broken down using De Morgan's law into not A times B times C, right? There's only one order triple that could possibly make this true because there's no or operator here. It's just one set of Boolean bits, I guess you can call it. This is just one set of like triplets, one set of bits that make up a singular triplet. Oh my gosh, that can make this true, right? And that's when A is going to be 0, B is going to be 1, and C is also going to be equal to 1. The answer to this is going to be A. All right, number 8. What single gate can be placed in the digital diagram to replace the rectangle so that all the inputs make the circuit true? Let's start by just simplifying and getting to the single gate first. So we have this one is just going to be A times B. This one is going to be B plus C with an extended not bar over top. That is going to be simplified using De Morgan's law to not B plus not C. Now, to make this true, the possibilities for this first half of the gate or this first input are when A and B are both equal to 1. So that gives us 1, 1, 0 and 1, 1, 1. The possibilities for this second input to be true are when B or C are equal to 0, right? So that's going to give us, I don't know, um, when they're both equal to 0, so 0, 0, 0, 0, and then 1, 0, 0. We also have the option of, let me get this because I fear this is just going to get long. We also have the option of when B and C are 0 and 1, and also the option when B and C are 1 and 0. And finally, actually that's it, right? Because we can't have them both be one. So if we were to use an AND operator, that would allow any combination, any overlapping combination between these two sets of triplets to give us an output that is also true. If we were to put an AND gate here, right, only 110 would be an acceptable, or only 110 would allow it so that the inputs make the circuit true. Let's put a 1 here. If we were to put an OR operator, we can just combine the total sum of the total number of triplets that we have across both boards, eliminating any duplicates. We only have one set of duplicates, so that's going to give us a grand sum of 7, I think. Is it going to give us 7? Hmm. Maybe not. Why would it not give us 7? Did I do this wrong? Oh my gosh, I did this wrong. I'm so frazzled today. Jesus Christ. I'm sorry. The logic is correct, but like my brain is not there. Okay, my bad. What am I saying? It's this. The Morgan's law is going to simplify to not be Nazi. My bad. I'm sure you guys are all like just listening to me yap and you're like, what is she on about? Okay, anyways. So the only time this is gonna be true is 110 and 111. The only time this bottom one is going to be true is if B and C are both equal to 0, right? So it's going to be 0, 0, 0, and 1, 0, 0. If we were to do an AND operator, I think mm, nothing would make it true. Yeah, there's nothing that would make there's no like there's no input that would give us a true value. So and is just going to give us a total of 0, or it's going to give us a total of 4 because there's no overlap between the two. Not and is going to give us the opposite of and. So we have a total of 8 inputs. If 0 of them work with the and gate, then 8 of them are going to work with the not and gate. And then same thing with the nor. It's going to be just the opposite of the or. Out of these four numbers, the not and gate gives us the greatest number. So that's going to be the answer. The answer to this is C. Number 9, prefix, infix, postfix. Define blah, 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 blah. Evaluate the following prefix expression. Numbers are single digits. Okay, prefix expression. That means we're looking for operator, operand, operand. We have number sign 2, 5, number sign 4, 1, number sign 1, 3. Number sign is going to be a to the b power plus b to the eighth power. So that's 2 to the fifth is 32 plus 5 to the second is 25. Man, I don't even have like the energy to do mental math right now. We're pulling it. Calculator for that. What did I say? 32 plus 25. That's going to give us a grand total of 57. This one is going to be 4 to the first power plus 1 to the fourth power. So that's just going to be 5, right? 4 plus 1. And then 1 to the third plus 3 to the first is 3 plus 1, which is 4. Then we go again. We have a division 57, 3. We have a plus 4, 1. This one's going to be 5. That one I can do. 57 divided by 3 is going to give us a grand quotient of 19. And we keep going. We have a plus 19, 1, 20. And we have minus 25 to give us 15. And finally, division 15, 5 to give us a grand final answer of 3. The answer to this is going to be B. All right, number 10, convert this infix expression into postfix if the square root of x is equal to x to the power of 1/2. Well, first of all, I hope you guys all already knew that. And secondly, when we're concerning square roots, like they kind of made it simpler for you by showing you what the infix version looks like. But there's two different operators that you need to keep track of here, right? The first thing is the 1 divided by 2. Before we can even do the exponent, we have to make sure that in postfix we do 1, 2 division. And then if we wanted to do x to the power of 1/2, that would be x raised to the power of 1/2, right? So just keep that in mind. Other than that, let's do this. So before we do any division between the numerator and denominator, let's do the numerator first, right? Before we can do the a plus, we need to do the square root, and before we can do the square root, we need to settle the b squared minus c inside. So we're going to start with the b squared. That's going to be b2 raised to the exponent. That's going to be subtracted from c. So once we subtract it from c, so this entire thing is our x, right? This entire thing is going to be raised to the power of 1/2. And like I said earlier, before we can raise anything to the power of 1/2, we need to first do the 1/2. So that's going to be 1/2 division. We have this divided by, not divided by, sorry. We have our base raised to the power of our exponent here. So that's going to be everything concerning the square root. To finish off our numerator, we're going to add this to a. Recall that a does happen on the left-hand side, so make sure you guys are writing that correctly in your post-it expression. And we're going to write a plus at the end. On the denominator, we have 3 times d. That's simple enough. It's just 3d with a multiplication sign at the end. And then finally, we are dividing the two of them because it is a fraction. So let's take our numerator, let's take our denominator, and let's just divide the two of them. That leaves us with a final answer of AB2 exponent C minus 1, 2 division exponent plus 3D times division. That is going to be answer choice D. Number 11, evaluate and express the answer in octal. So we have two hexadecimal, what? Okay. We have two hexadecimal inputs here. This isn't like an addition or subtraction operand. This is an OR operator, right? Which basically means we need to convert this into binary, right? The only thing that you guys know how to OR values with are zeros and ones. So let's convert this all into binary first. I'm gonna type this one. So remember when we're converting from hexadecimal to binary, we're going to take each hexadecimal digit and split it up into a 4-bit binary string. So 3 is going to give us 0, 0, 1, 1. B has the numerical equivalent of 11, so that's going to be 1, 0, 1, 1. 4 is going to be 0, 1, 0, 0. And then A is going to be 10 or 1, 0, 1, 0. Now, please just make sure you guys are keeping track of leading zeros. They're important. Okay, now for the second half, we have 9D to E. 9 in binary is what? 1, 0, 0, 1. D is going to have the equivalent of 13, 10, 11, 12, 13, 18. Yeah, 13, right? So that's going to be 1, 1, 0, 1. 2 is going to be 0, 0, 1, 0. And then finally, E is going to be 1, 1, 0, 0. And the two of these are going to be being, and these two binary bit strings are going to be ORed against each other, which gives us a final answer of 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, right? When we are taking a binary string and we want to convert it into octal, starting from the right-hand side, we're going to split it up into groups of 3. And we're going to add any leading zeros as necessary. 0, 0, 1 in octal is 1. 0, 1, 1 is going to be 3. 1, 1, 1 is going to be 7. 1, 0, 1 is 5. 1, 0, 1 once again is 5. And then 1, 1, 0 is going to be 5. No, 6. Yeah. So our final answer is going to be 137556, which is answer choice B. Number 12. Starting at the number 2021 in base 10, find the next lower year number whose binary representation has 4 consecutive zeros. Okay, well, first things first, let's convert this base 10 number into binary. And we can do that easiest by using just the ladder method, I guess. So 2020 divided by 2 is going to give us 1010 with the remainder of 1. 1010 is going to give us, I don't know, like 505. Yeah, it's going to give us 505 with a remainder of 0. 505 divided by 2 is going to give us 252 with a remainder of 1. 252 divided by 2 is going to give us a number that I'm calculating right now. 126 with a remainder of 0. 126 divided by 2 is 63 with a remainder of 0. 63 divided by 2 is going to be 31, remainder 1. 32 divided by 2 is 15, remainder 0. Sorry, not 0, 1. Yeah. 15 divided by 2 is going to be 7, remainder 1. 7 divided by 2 is 3, remainder 1. 3 divided by 2 is 1, remainder 1. And then 1 is obviously our binary number that is allowed. So we're going to stop there, and we have our binary number. So we have 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, yeah, 6 ones, followed by 2 zeros, 1, 0, 1. This is going to be our binary number. Now, from this, we're just going to keep increasing this binary number until we can come up with a number that has 4 consecutive zeros, right? So, I don't know. If we were to increase this, wait, 1, 2, 0, 0, 0. Yeah, okay. Let's just increase this slowly 1 by 1. If we were to add 1 to this, then this would become 1, 0 like this. No 4 zeros. If we were to add 1 again, it would become that. If we were to add 1 one more time, we'd be left with this. If we were to add 1 again, it'd be that. Oh, no, I'm dumb. Sorry. Make sure you guys are reading carefully because I totally did not there. It says find the next lower year number. So we're supposed to be going backward, right? My bad. Mm, okay, sorry. If we're subtracting 1, we're left with this. If we subtract 1 again, we're left with that. Subtract another 1. Subtract another 1. We're left with 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1. That is going to be the binary number, the next lowest binary number that has 4 consecutive zeros. So if I were to convert that back into base 10, that's actually going to give us 2007 if you guys were keeping track. You could obviously, break up each digit into and assign it its value, like 2 to the 0, 2 to the first, 2 to the second, etc., etc., etc. Or you could have just kept track how many times I subtracted by, which was like 4. Let's actually do it one more time again, just to make sure. Right, so this is -1. I'll use like dashes to keep track, right? We subtract one more time, we're left with this, so that's 2. Subtract one more time, we're left with this, that's 3. Subtract one more time, we're left with this, that's 4. So if we originally started at 2021, subtracting 4 years would have given us 2017, and therefore the answer to this is going to be. All right. Number 13, we also went over this yesterday, but just for completion's sake, let's go over it again. Is given a queue for receiving the COVID-19 vaccine queue. Only people with names starting with a consonant are placed in the queue, and when an asterisk appears, 2 people on the queue receive the vaccine and are removed. So basically, we're going to go through this left to right. If we see a vowel, we're not going to add it to the queue at all. If we see a consonant, we add it to the queue. If we see an asterisk, we're going to remove 2 units from the queue. Now, keep in mind, when we are popping from a queue, we are removing things from the front, not where we added it from the other side. So we have A is a vowel, so we don't count that. We have C, then CS, then CSL. Asterisk gets rid of the C and S. Then we have F for finals. We skip the I, we have LFN. We skip the A, we have LFNL. And then we have LFNLS. Asterisk, one set of asterisks gives us NLS, another set of asterisks gives us just S. Then we have C in competition, we skip the O, we have SCM for competition, and we have, we have SCM for the M in competition, then we have SCMP, we skip the E, we have SCMPT, we skip the I, we have SCMPPT, skip the other I, skip the O, and then we have SCMPTTN. 3 sets of asterisks. The first one is going to get rid of the S and the P to give us MPTTN. The second asterisk is going to get rid of the MP to give us TTN. And the third one is just going to give us N. Next, we have the word this. So we add T, we add the H, we skip the I, we add the S. One set of asterisks, we skip the HS. Then we have HS in the word year, we have HSY. We skip the E and the A, we're left with HSYR. Final set of asterisks is going to get rid of the H and F and give us YR, right? And then if this is what the queue looks at every single point in time, the question asks what is the longest length of the queue at any point if they enter the queue, blah, 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 blah. That is going to be right here at SCMPTTN, which has a length of 7. That is going to be our answer. I feel like all of the answers so far have been like B or C. All right, number 14, data structures. What is the pre-order traversal in the binary search tree for the word pterodactyl? Okay, let's make our binary tree first. We have P. T is going to come after P. E is going to come before. R is going to be Q, R, S, A, L, M, N, O, P, Q, R. It's going to come after P, but before T. Oh, Lord, another one. Q, R, S, L, M, N, O, P. Okay, O is going to come before P. So it's going to come before P, but after E. So it's going to go down here to the right. D is going to come before anything we've seen so far. A is going to come even before that. C. C is going to come before P, before E, before D, but after A. Another T is going to go to the left of the pre-existing T and then to the right of the R. Y is going to obviously come after everything else. And then finally, L is going to be before P and then after E and before L. So this is our binary search tree, assuming I made it right, which I did. This is our binary search tree, and this is asking for a pre-order traversal. This is okay. Pre-order traversal down here. A pre-order traversal is going to go in the direction of root, then left, then right, right? So if we go back to here, we're going to start with the left tree, and I'm going to try and make this as least discussing as possible. But the left node gives us this tree. Then we need to find the left node of this tree, which is going to be this. The left node of this tree is still complicated, so we're going to go down into this. In which case, there is no left node. We have a root and a right, but we don't have a left node. Oh, wait. It starts with root. Oh my gosh. I'm sorry. Okay. Root. We got rid of the root. Now we're working on the left. Okay. Anyway, back to the green here. So now we have A and C. A is our root, C is our right, and then we have no left. Oh, great. We have one for each one. Our root is going to be A. There is no left, and our right is going to be C. We are done with the green. Going back out to the light blue, right? Wait, no, I messed this up. Oh, I gotta learn how to read, guys. I'm sorry. Okay, sorry. Root, left, root is here, is E. Left is here. So we need to go even further in. Root, left. We need to go even further in. Root is going to be the A. There is no left, and the right is going to be C. So we're now done with that dark green mess, or whatever color it is. Right? That brings us back out to this red one here, where we wrote the root down, right? We had C. We did the left-hand side, and there is no right-hand side, so we're done with that as well. Going back out to the lime, we already wrote down the root, which was E. We did the entirety of the left-hand side, which was BAC. And then the right-hand side leaves us with O and L, right? That's two different nodes. So when we go in, we have to go deeper in, where the root is then going to be O, the left hand is going to be L, and there is no right-hand node. Once we're done with that, we're done with the entire left-hand side of the branch, so we can move on to the right, right? Once again, we are following the root left-right pattern. Okay, now I'm paranoid that, okay, yeah, no, I we're still following that root left-right pattern, so the root is going to be T. The left is composed of two nodes, R and T, so we're going to go deeper in. Deeper in, we see that the root is R, there is no left, and the right node is going to be T. Once we exit this, we're done with our left-hand side, and we have to move on to the right side. Thankfully, there's only one node in here, so we can just write that down as. And that's it. We're done with our pre-order traversal. So we have a final answer of PEDACOLTRTY, which is going to be answer choice. All right, number 15. Given the directed graph below, how many unique pairs of vertices do not have a path of length 2 in either direction? Okay. Unfortunately, we cannot take shortcuts here, right? We would have to just map out the entire thing, which is so annoying. So vertex A can go to B, C, and E. B, C, and E. Vertex B can go to just C, I believe. Vertex C can go to D. Vertex D can go to A and just A. And finally, vertex E can go to A, C, and D. So this is what our path length matrix, path length one matrix is going to look like. I'm just making sure that I didn't mess this up, which I don't think I did, so yay. All right, let's write it again because we need to have a matrix concerning path length two. So we're just going to repeat this. This is going to be 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 6, 0, 1, 0, 1, 0, 0, 0, and 1, 0, 1, 1, 0. Okay, let's multiply our two matrices together. Right. You guys understand the drill. It's going to be rows and columns. Um, yeah, I'm not gonna go over how to multiply a matrix unless you guys absolutely want me to. So, speak now or forever hold your peace. But assuming that you multiplied everything correctly, your path length two matrix is going to look as follows: 1, 0, 2, 2, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, and finally 0, 1, 1, 0, 1. Oh no, not finally. This is finally. Last row is going to have 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Now this question is kind of weird. It says how many unique pairs of vertices do not have a path length 2 in either direction? So when we are concerning all of the paths that don't have a path length of 2 at all, right? Let's just go through them. So everywhere you guys see a 0, that indicates that there is not a path of length 2 in that specific direction. So in that first row, when we have 1, 0, 2, 2, 0, it's saying from A to B, there's no path length 2, and also from A to E, right? Second row, B to A, B to B, B to C. Third row, C to B, C to C, C to D, C to E. Fourth row is going to be D to A, and then D to D. And then E has a path of 2 in every single direction. So we're not concerned with that. Now, out of this list, we then need to narrow it down to pairs of vertices. Pairs of vertices indicate paths where it goes in either direction. So we're talking about things like ABBA or AEEA and things like that. And this also includes our paths that start and end at the same vertex, so like CC, right? What about ABBA? We have an AB, we also have a BA here, so that's one possible answer choice. We have an AE, but we don't have an EA, so that's not going to be considered in our list at all. We have a BB, that counts because it's a double. We start at B, we end at B. Even flipped around, the other path is still going to be from B to B. We have BC and CB, so let's get rid of that. We have CC, that's fine. We have a CD, but we don't have a DC, so let's get rid of that one. We have a CE, but no EC, so let's get rid of that one. We have a DA, but we have no AD, so we're also going to get rid of that one. Our final one is a DB, but because that one is like starts and ends at the same place, that one's perfectly fine. That leaves us with a total of 5 different pairs of vertices that don't have a path length of 2 in either direction. The answer to this is going to be C. Number 16. How many cycles from A are there in the directed graph? Same graph as in number 15. Okay, lovely. That takes all my work out. Let's just pull open the matrix that I already made. We only need this first one, and I'm going to be rewriting it anyway. So starting from A, okay. Starting from A, we have A can go to B, C, and E. Right? B is gonna go to just C. D can go to just C, D can go to A, and then E can go to A, C, and D. From here, we just need to create a list of cycles that start from A, right? Is that on the right-hand side here? A can branch into B, C, and E. B can branch to C can branch to D, E can branch to A, C, and D. So A is the end of a cycle. Let's circle that. C is fine, D is 5. C can branch to D, D can branch to A, so this is the end of the cycle here. So it's also going to branch to A, obviously. This one will also branch to A. So we only now have one more path to deal with. D can branch to D, and then D can also branch to A. Oh, that was nice and easy. That gives us a total of 1, 2, 3, 4, and 5 cycles to deal with. The answer is going to be C. Number 17, what does this program do? In order to have this program print the three inputted numbers in increasing order, one must be in the blank below. So we have three variables here. It's kind of like, imagine like using a scanner. It says input A, B, C. And then three if statements, right? It says if A is greater than B, then we're going to swap the values of A and B. We're going to end our if statement. If B is greater than C, then we're going to swap B and C. Oh, we don't even care about that. Okay, and then the last part, if blah, 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 and we have to input one of these four conditions, then we're going to swap the values of the two variables being compared, and if output A, comma B, comma C. Um, kind of weird. Hold on. Okay, well, I guess you could just plug in chug for this one. I don't know. There isn't really much thought to this, I suppose. Um, okay, well, first things first, let's get rid of answer choice, right? Answer choice D is completely irrelevant. We have in our second if statement, we have if B is greater than C, then swap B and C. After we swap them, right, we've essentially guaranteed that B is less than C. So why would we want to swap them back? This basically ensures that B is going to be less than C. Once we get down to the third if statement, right, we don't want to recheck that B is less than C and then swap them again. That kind of defeats the whole purpose of the second one. So let's get rid of answer choice C. Answer choice C is never going to come true. This one also does not work, right? Answer choice C has the same condition as our second if statement, right? If B were to be less than greater than C, right? Let's say it's like 5 and 1, and we swap them, so B is equal to 1 and C is equal to 5. We've essentially guaranteed that B is always going to be less than C. Therefore, the condition for C will never even come true. So that's also not an option. If we look at the last two, if we look at the last two, based on the first one, what have we guaranteed? We've essentially guaranteed that A is going to be greater than B. No, sorry, A is less than B. I guess logic requires. Okay, we've guaranteed that A is going to be less than B at the end of this if statement. What about at the end of at the end of the second if statement? Well, at the end of the second statement, we've guaranteed that B is going to be less than C, right? As I've already stated before. However, okay, I'm gonna try to explain this in a way that makes sense because it's like in here. The problem is I need to get it in your guys' brains. Okay. When we swap the first two values, right? And we guarantee that A is less than this second value, we have no guarantee that A is smaller than this value, right? If C happens to be the smallest number, let's say we have something like originals of, I don't know, 3, 4, and 1, right? Or let's actually do 4. We have 4, 3, 1. A is greater than B. We swap them. This now becomes 3, 4, and 1. We have another if statement. B is greater than C. 4 is 1. That's true. So we then swap the values of B and C, and we're left with 1 and 4. The problem is we've never checked and compared the values of the original A and the original C. The variable names get a little convoluted here because we're constantly swapping values around. So hopefully these like placeholder values give you something a little bit easier to look at. But at the end of the day, we've never looked at, again, the original values belong to A and C. We've never compared the two of them. It's just once we get to that third if statement, it's not that they're no longer in the positions of A and C. Instead, they're in the positions of A and B. Oh, wait, no. Sorry. I think it's these two that have never been compared. Because you compare these, you swap them, compare these, you swap them. Yeah, yeah, yeah. Basically, we've never compared what was originally B and what was originally C. It's just assuming that we've swapped it out multiple times, right? And assuming that everything is in presumably the right order. At the end of the day, we have to once again recheck what is now variables A and variable B and swap them if necessary, right? In a case like 3, 1, 4, obviously the 1 should be coming before the 3, and therefore we need to check if the value of A is greater than the answer to this is going to be, the answer to this is going to be A. When you guys are doing a problem like this, right, where it's just like a series of if statements, one thing you guys can do as an effective enough strategy is kind of just plug in all the conditions that could possibly be, right? And the conditions are when the order of A, B, and C, I'm just going to use like 1, 2, 3 as examples, is if they're already in order, 1, 2, 3, if A and B are swapped, 2 and 3, if A and C are swapped, I fear I'm going out of order. 3, 2, 1, right? Okay, wait, no, sorry. I'm gonna make this a little easier to write. Okay, so 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Right? So these are the 6 possible conditions that we can input in the value in that specific order, where A is originally the left-hand column, B is originally the middle column, and C is originally the right-hand column, right? In instances like this, we are going to be, there's only 6 conditions here, right? If you plug them in one by one, and see what works, you will eventually end up with the right answer. Not to mention, we don't even have to check all of them, right? We don't need to check A, B is greater than C, and B is less than C. We don't need to check those 2 conditions, like I said earlier, because logically we can determine that they're useless. They don't do anything, which kind of just narrows down your answer to A and B. So between the 2 of them, right? Let's assume you have to run through this program 12 times. That's very, very manageable, right? Anyways, those are just tips and tricks and strategies to solve this problem. At the end of the day, answer is going to be A. All right, number 18. After the following list of programs run, what is the value of the last expression? Oh boy. Okay, let's write this all out. We have P and RO, G, RA, G, RA, MM, I, G. Did I do this right? Yeah, I did this right. Okay, let's underline. We have P as our first element, RO as our second element, GRAMMI as our third element, and then NG as our fourth. We have a CDDA, so we're gonna go from the right and work our way left. That's gonna be a CDR, 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 and CDR. Okay, I'm just going to edit this as I go along. A CDR dictates that we are going to get rid of everything except for the first element, and not get rid of, oh my gosh, we're going to pull out everything except for the first element and then place a pair of parentheses around. That's going to leave us with this. If we were to re-underline, it would look something like this. Another CDR, we're going to do the same thing. So we're going to pull out everything except for the first element and put a new pair of parentheses around it. That leaves us with Grammy and Ning. So where this is going to be our first element, this is going to be our second element. Then we have a CAR. So we're going to only pull out that first element. We'll get rid of all of this. And our parentheses are also going to change. These are a new set of outermost parentheses. Oh, these are a new set of outermost parentheses. So if we were to underline, G is going to be our first element. RA is our second, MM is our third, and then I is our last one. We have two more CDRs to go, so let's get rid of the G. That's CDR number one. And then let's get rid of the RA. That is going to be CDR number two. And boom, we're done with our Lisp program. Answer is going to be B. Number 19. FSAs. Given the regular expression, which of the following strings are not accepted? Okay. Well, first things first, everything here should be ending with a CS or a Y, which everything does. So assuming that everything ends with a CS or a Y, if we see that, we're going to just kind of cross it out because we're not even going to consider it in the evaluation of the rest of our FSA, or sorry, in the rest of our strings or whatever. Y, Y, S, and Y. Okay. The rest of it, we should have a string of letters that originates in the first half of the alphabet, followed by a string of letters that are contained within the restraints of E and U. And if it doesn't follow that order, then the string is not going to be accepted. So starting with history, LMNPIJKL. So starting with the first one, H and I belong in that first half. S does not. So starting from S, we're assuming that everything falls in the EU category. Does S fall within that category? URSTUV. Yeah, it does. S fits, T fits, O fits, R also fits. So A is okay. History works. What about classics? C, L, A. Those three letters fall within A through L, so that's fine. Then we have S, S, I. All three of those fall within EU, so this is also fine. We have physics. P doesn't fall within A through L, so we're assuming that everything afterwards is going to fall within E through U, right? So P falls in E through U, H also falls there, Y does not, right? So C is going to not be accepted. And obviously, if our string is not accepted, that's one of our answer choices. Then we have botany, B falls within A through L, O does not, so starting from now, we're assuming everything falls within EU. T falls in EU, A does not, so D also is not accepted. Let's look at E. G, E. Both of those fall within AL. Everything after should fall within EU. O, M, E, T, and R all fall within that. So this one's accepted. Chemistry, C, H, E. The first three letters fall within AL. M falls within EU. I falls within EU. S, T, R all fall within EU. So F works. Mathematics, we have M, A. Those two fall within AL. Starting from T, though, we have to make sure it falls within EU. So T, H, E, M. A does not, so G also fails. Biology, we have B, H, I, J, K, L. B, I, those two letters fall within AL. O does not, so we're going to assume that everything following falls within EU. O, L, O, and G, those all fall within EU, so this one is also accepted. The three strings that are not accepted are going to be C, D, and G, which is going to be answer choice B. Answer to number 19 is B. Okay, last problem, assembly language. What is printed when the following program is run if the data is 6? Okay, if the data is 6, we see a read command here. That basically means we're establishing a variable n with the value of 6. We don't see any more reads here, so that's pretty much the only one. There's going to be more variables other than these two. I can tell just by looking at the rest of this, but for now, let's establish that. And then on the right-hand side, let's do some work. So S is declared as 0, N is declared as 6. We're gonna load N, divide by 2, and store this in F. If it's equal to 0, which it is not, we would go to SB, but it's not, so let's skip that. We're gonna load N again, divide by F, multiply by F. If it's less than 0, we would go to next, but it's not. So let's load F, add F, store this in F. Next, we would load F, subtract 1, store this in F, and then we would go back to the top and repeat. So BE is not true. So we load N, divide by F, divide by F, multiply by F, use the 6 again. Subtract N to give us 0. It's not less than 0, so we move on to load S, load F. No, sorry, load S, store this in S, load F, subtract 1, store it in F, and go back up to the top. Where do I feel like I'm doing this wrong? Okay, we're gonna load N, divide by F, which is 1, so that just stays at 6. Multiply by F, give us 6 again. Subtract N to give us 0. It's not less than 0, so we're gonna load S, add F, store this in S, then load F, and then go back up to the top. Where we skip B because it's not equal to 0. We're going to load N, divide by F, multiply by F, subtract N. It's not less than 0, so we're going to load S, add F, store this in S, subtract 1, store it in F. Then we go back up to the top. We load N, divide by F, which gives us 1, multiply by F, give us 4, subtract N to give us -2. -2 is the value that is less than 0, so we're going to just move down to next, where we're going to load F, subtract 1, and store this at F. So it's F. Then we're going to go back up to the top, where it's not equal to 0, so we're going to load N again, divide by F to give us 2, multiply by F to give us 6, subtract N to give us 0. It's not less than 0, so we're going to load S, add F, with 8, I forgot where I was, and then store this in F, right? Add F to us, yeah. And we're gonna load F, subtract 1, and store this in F. Back up to the top, it's not equal to 0, so load N, divide by F, multiply by F, subtract N, load S, add F, store this in S. Store this in S, load F, subtract 1, store this in F, go up to the top. Load N, divide by F, multiply by F, subtract N, it's not less than 0, so we're going to load S, add F, store this in F, load F again, which is 1, subtract 1, and store this in F. We go back up to the top where it is equal to 0. No, I definitely did this wrong. Where did I go wrong? Oh, I hate it. So annoying. Okay, I feel like I just wasted 5 minutes. Man, I don't really want to do this. Um, okay, ooh. Yeah, anyways, this would have outputted 11, and that is not the answer. So we're gonna redo it. Uh, so fun. I'm having a great time. Okay, sorry. We read n, sorry, s is declared as 0, n is read as 6. We're gonna load n, divide by 2 to give us 3, and we're gonna store that in f. It's not equal to 0, so we load n, divide by f, multiply by f, subtract n, load s, add f, store this in f. And we're gonna load f, where's f? Subtract 1 and store it in f. Go up to the top. It's not equal to 0, so we're gonna load n, subtract, no, sorry, divide by f, give us 3, multiply again, give us 6, subtract n to give us 0. Did I mess up? No, I don't think I did. Give us 0. I hate this. It's not less than 0, so we're gonna load s, add f, store this in s, load f, subtract 1, and store this in f. Okay. Then we're gonna go back to the top. Not equal to 0, so we're gonna load n again. Divide by f, give us 6, multiply by f, give us 6 again. Subtract n to give us 0, subtract n to give us, no, wait, I've already subtract n. It's not less than 0, so we're going to load s, add f, store this in s, load f, subtract 1, store in f. Then go back up to the top. It is equal to 0, so we're just going to go down here and print that, which is it. Wow, I don't know what I was doing earlier, but clearly it was not correct. Yeah, the answer to this is just going to be C, which is 6. All right. Any questions about the 2020-2021 intermediate classroom division set of problems that we just finished? I hope for those of you guys who did not get 100, which is every single one of you, you guys were at least listening to the ones that you got wrong. You understand where you went wrong and you understand the question itself. And for those of you guys who are taking other divisions, I hope you were able to follow along. Again, whatever concept you got wrong, I hope it was a little helpful to go through this again today. All right. If nobody has any questions in the last 17 minutes of class, I have some concepts that I do want to go over with you concerning computer number systems. I forget which ones exactly. Okay, first things first. Computer number systems dealing with binary numbers, not even binary numbers, concerning ourselves with decimals here. Okay, so this one, it says solve for the following for x in base 2. We have 24 in hexadecimal times a mystery number in binary, plus 41 in octal is equal to 2 times 110 plus blah, blah. Okay, first things first, because we have multiplication and just multiplication actually. Because we have multiplication involved, we should convert all these to their base 10 numbers. So 24 base 16 is going to be 4 plus 2 times 16 is 32. This is going to have a value of 36. We don't know what this x is. 41 in octal is going to be, I don't know, 1 plus 32 is 33, I think. 2 in octal is 2 in base 10. 110 in base 2 is 6, I believe, in base 10. And then 1b16 in base 10 is 27. So if we were to solve this out, we essentially have 36 times x plus 33 is equal to 12x, I did 2 times x plus 54. So if we're solving for x, this is basic algebra, right? We have 24x is equal to 21, 20, yeah, 21. And therefore, x is going to be equal to 7 over 8. Now, This is a problem. You guys don't know how to convert 7/8 into binary. No worries. I am here to teach you exactly how to do that once I remember how to. Okay. The concept is very, very similar, right? When we are converting from base 2 back into, sorry, when we're converting from binary back into base 10, right? Or I guess between the two, it doesn't really matter, right? You guys remember how we had to like do this thing where if it was like, oh, 0, 1, pick a different one. We had like 1, 0, 1, 1, 0 or something like this, right? The way that we converted back to base 10 is by assigning each one to a value of 2 to whatever power in an increasing order, right? So in a case like this would be 1 times 2 to the fourth plus 1 times 2 to the second plus 1 times 2 to the first, and then you add them all up. Decimals is the exact same concept. It's just after the decimal, right? We're going to go in the reverse. So this is going to be 2 to the negative second, then 2 to the, sorry, 2 to the negative first, then 2 to the negative second, and 2 to the negative third. And this is actually going to go on and on and on and on and on and on. But for the purposes of 7/8, this is pretty much all we need, right? This is the same thing as saying 1/2. This is the same thing as saying 1/4, and this is the same thing as saying 1/8. So to get a total value of 7/8, right? Let's just erase all of this from now on. To get a total value of 7/8, what do we need to add together? Well, we need to add together a 1/2 that gives us 4/8, plus a 1/4 that gives us 6/8, plus a 1/8 that'll give us a sum of 7/8. And that's it. That's how we convert from a base 10 fractional value to its binary equivalent. That's why the answer to number one is going to be C. Any questions about how to convert between base 10 and base 2 when we're dealing with decimals? Nope. All right. Moving on to number two, it is a very similar concept, right? We need to convert a base 16 hexadecimal number to an octal number. How do we do that just completely ignoring the decimal? How do we do that just in general? Well, we need to first convert it to base 2. It's the exact same freaking concept, like completely disregard the decimal point. So if we have decimal 4, 2, right? In binary, this is just going to be 4 is going to turn into 0, 1, 0, 0. And then 2 is going to turn into 0, 0, 1, 0. Once we have that, we're going to start lumping this into groups of 3 so we can convert it to octal. Now, the only difference is earlier we were lumping in groups of 3 starting from the right. This time we're going to be lumping it into groups of 3 starting from the left, right? So it's basically we're going to start lumping from wherever that decimal point is. In the case of whole numbers, right, the decimal point is on the right, so we lump from the right. In the case of fractions and decimals, we're lumping things from the left. So this is going to be 0, 1, 0, 0, 0, 0, and then we have a 1, 0, and we need to add a trailing 0 here. It's the same concept, right? If you have like a decimal number of like, I don't know, 20.46, that's the same thing as saying 0.460. That's why we're allowed to add trailing zeros to the end here. 0, 1, 0 is going to give us an octal number of 2. This is going to be 0, and this is going to be 4. So 0.42 in hexadecimal in its octal form is going to be 0.204. Any questions about this?
Why would you add a trailing zero, not a zero at the beginning?
Because if we add a 0 at the beginning, it's going to shift everything and change the value of the actual number, right? Use this
So
as an
for
example. Oh yeah,
so
yeah,
for
sure.
decimals, you put in a trailing
0.
number, and then
Yes,
when
you put
it's
a
a
trailing.
regular like when it doesn't have a decimal, you just put it in the beginning.
Exactly.
All right.
Think of it like this. If you have like the number like 15, right? This is a whole number. What's equivalent to 15? 0, 1, 5, where we put it at the front, or 150, where we put it at the end. Obviously, this is going to be the equivalent. That's why for whole numbers, you place leading zeros. But for decimals, let's use the 0.46 example that I have up here. 0.46 is the equivalent of 0.460, not 0.046. So in that case, we would add a trailing 0. Does that make sense? Okay. So any other questions? All right. Let's skip down to number 7. This one asks how many different 1 byte values contain the bit string 00100. Um, I think the important thing to keep in mind here is when it says 1 byte, I believe a byte is made up of 8 bits. I think a byte is the bigger one. Oh, oops. I think it's bits of a byte. Yeah, this 1 byte is equal to 8 bits. So basically, this is saying if we have an 8 bit string like this, 1, 2, 3, 4, 5, 6, 7, 8, how many different configurations of the string where we can plug in zeros and ones will have like a bit string substring of 00100? That's the first thing that you need to understand. Okay, my bad. Someone's fire alarm was going off and it was annoying me. Anyways, so we have an 8 bit string here. It's the same thing as saying a 1 byte string. And we basically have to figure out how many out of these, 8 strings contain the bit string substring of 00100. Um, I think for this one, there's one, two, three, four different positions that the 00100 could possibly be in, right? So the first one is at the very beginning. If you have 00100, you have three asterisks where it doesn't exactly matter what these are. So this is going to be 2 to the third. There's a total of 8 different configurations where the 00100 is found in the beginning. How do we know that? Right? It's the same thing as the when we're solving in the bit string flicking, the A to the whatever, the ABCD thing, ABCDE thing, right? Three asterisks. Each one of them can be either a 0 or a 1. You have 8 different configurations. What if it was here? Same thing. Another 3 asterisks. So it's going to be 8 again. Same thing as if it were here. Yeah, so it's going to be another 8, and then finally it's going to be another 8 at the end. Now, we're not actually done here. Yes, we're not actually done here, right? So far we have a combined total of 32 strings, but 32 is not the answer. The answer is actually going to be 31. Why? Because we need to keep into account repeats. And when would repeats occur? Well, repeats would occur whenever we have symmetry. So in the case of 00100, if we were to finish this off with 100, this is a symmetrical string that occurs exactly the same as when our 0010 bit string is on the right hand side and our left hand side is concerned with 001 like this, right? So in the case of those two specific conditions, we do technically have a repeat. That is going to be the only one repeat we have because that's the only way that we are going to generate symmetry. So basically, if you want to figure out how many repeats, just figure out how many different symmetrical configurations you can make. Yes, you can make. So we're going to get rid of one repeat to give us a final sum of 31. Number 10. I think this is a very similar question. How many binary representations of the numbers from 2 to 2047 inclusive are palatines? Um, 2047, I believe it's like a 10-bit. I think it's a 10-bit. No, I'm lazy. But there you go. It's 1, 2, 3, 4. Oh no, I lied. There's 11 bits. So 2 is going to be in binary. That's going to be like 1, 0. And then 2047 is going to be this. That basically tells us the reason why this is important is because of the number of bits that we are concerning ourselves with, right? That basically tells us we can start from, or we can start checking for palindromes from when they have 2 digits, when they have 3 digits, when they have 4 digits, all the way up until when they have 11 digits. 2, 4, 5, 6, 7, 8. It also says lead digits cannot be zero. So for each one of these like different number length, string length, just figure out how many palindromes can possibly exist where the lead digit is not zero. When we have a two-bit string, a string length of two, right? We only have one option, right? That's just going to be one one. We have one option here. For three, for a bit string length of three, we have 101 and we have 111. So that's going to have a sum of two. For the four would be a very similar concept where it's either going to be 1001 or 1110. Oh wait, no. 1111. Oh, why that looks weird, right? Okay. And we're just gonna kind of keep on going with this pattern. Now, once we get the kind of like the bigger numbers, like let's say five, for example, one, two, three, four, five. The starting and the ending has to be one. But as for the middle three, right? Just figure out how many different possible palindromic combinations of three there are. You already know of two that exist, right? The ones that are concerned here in the earlier one. So you can just check back on the bit string length of three to see how many palindromic string length three ones there are. But in addition to these, right, you just have to be careful of the fact that these are only taking into account the palindromes where the lead digit is not zero. In the case of five, that middle string can have a leading digit of zero. So this could be like 11111 or 11011, right? Where the middle string is composed of the two that we've already established for a bit string length of three. But we can also concern ourselves with 10001 and also 10101, right? These are another two options. I'm like pretty sure it's just gonna double every single time. So in a case like this is going to be four or like double whatever it needs to be. Let me actually just mathematically make sure that is the case. So we have one plus two plus two, five. I should un momento, por favor. I am checking something. Yeah, it's basically just going to double every single time. What I mean by that is when you compare like bit string length of five and a bit string length of three, for example, right? It's gonna double because the palindromes that you can possibly generate for that middle section are always going to be exactly the same, except for the part where the leading zeros or the leading and the ending ones are going to be changed to zero. So but once again, if 101 is an option, that also means 000 is an option. If 111 is an option, that means 010 is also an option. So for every single like pairing, where like 5 3 6 4, it's essentially going to double in length. If we had like a bit string length of seven, 1 2 3 4 5 6 7, right? To figure out how many palindromic strings we can make, we just need to take a look at how many palindromic strings we can make of a string length of five. With five, we've already established that we could make four where the leading digit cannot be zero. So take that four, we double it, and we've essentially made eight palindromic strings of string length seven. And if we add this all up, we are ending up with 1 plus 2 plus 2 plus 4 plus 4 plus 8 plus 8 plus 16 plus 16 plus 32 for a final sum of 93. It's actually pretty cool. You guys can like draw it out on your own time to see if I'm, lying or not, but I'm not. 11 is the last one that I wanted to kind of just go over, and it's a very, very similar question to, I believe, like number 7. Does the ECSL hardware engineers have recently developed a 5-bit memory chip using radical new biotechnology? Unfortunately, the chip melts whenever a value containing the pattern 101 appears within the 5 bit. Of the 32 possible values that the chip can hold, how many will cause the chip to melt, right? Of the 32 possible values, how many contain the pattern of 101? Honestly, if you wanted to, you don't even need to do all this. You could just write out all 32 and then see which one of them has 101. But yeah, basically, if we were to add like 101 here, right, we have two asterisks, so that's a total of four. We have 101 in the middle, another two asterisks, that's another four. And then obviously 101 on the right-hand side is going to give us another four. Now, this gives us a total sum of 12, but just like in number seven, we have to keep in mind palindromic repetitive bits. So if we were to fill this with 01, it's the same thing as saying, it's the same thing as if the 101 were contained on the right-hand side, right? And we had a 10 fill in the same blank. So in a case like that, we have a repeat set of a five, we have a repeat 5-bit string, subtract one, this gives us a total of 11 different bit strings that the chip cannot hold. All right, so that brings us exactly to 8:30. Any questions concerning these? The last three problems that I went over, they were more just like so you recognize them, and if you see anything similar to them, you don't freak out. I am more concerned about the fact that you guys know how decimal binary numbers work. So, any questions about any of this stuff, whether it be the computer number system here, the second worksheet that I'm pulling up, or again, going back to the 2020, 2021, any questions about this? Yes, no, maybe so. All right. If not, then we're going to end class here today. Tomorrow is going to be the last day of practice. Also at 7 p.m. We are going to be going over the final year that I don't think I've covered, which is 2019 to 2020, or the 2020 finals, whatever you want to call it. So come prepared for that. And then on Saturday, you guys are going to take your final test. That's all I have for you guys for today. If you guys, again, have any questions that you don't want to ask right now for whatever reason, feel free to say. Otherwise, you guys are free to go, and I will see you tomorrow.